Welcome to Tomorrow Unveiled, where we take the chaos of the present and extract the clear signals of the future.
And this week, those signals are, well, they're pretty loud. We're not just seeing small updates.
No, not at all.
Our research team's analysis really confirms it. We're looking at the simultaneous unveiling of, like, the entire tech stack for what's coming next in computing.
Yeah, it feels like a real shift. We've spent, the last couple of years in that sort of model magic phase, seeing all these cool demos.
Right, the flashy stuff.
Exactly. But now the analysis shows we're deep into this strategic industrial build-out. It's like moving from showing off a prototype car to actually building the highways, the factories, the whole system needed to make it work at scale.
That's a great analogy. And our mission today on Tomorrow Unveiled is to walk you through that build-out. We've identified really 5 key interconnected layers that are all coming into focus right now.
Okay, so what are they?
We're talking infrastructure, the absolute foundation. In the architecture, how it's built, the standards needed, the big applications emerging. And finally, the user interface, how we interact with it all.
And we're drawing on some heavily corroborated findings here.
Yeah.
Right, this isn't just speculation.
Not at all. This is based on where the big money, like tens of billions, is actually flowing. We'll show you how AI is fundamentally reshaping computing itself from servers to quantum bits.
And maybe critically, why things like governance, accountability, even energy use, they aren't optional extras anymore. They're being hard-coded into the systems.
Exactly. So if you want the inside track on the physical, the financial, the strategic bedrock of what's next, well, this deep dive on Tomorrow Unveiled is definitely for you.
Okay, let's start right at the bottom layer then. Infrastructure. You said it's the foundation, and it sounds like the rules of the game here are changing fundamentally.
They really are. The core finding our research team zeroed in on this week is that access to infrastructure. That's the new moat. It's not just about having the smartest algorithm anymore.
It's about having the hardware to run it.
Precisely. And the headline number that screams this is this massive $38 billion partnership. It's a multi-year deal between one of the leading AI labs and Amazon Web Services, AWS.
$38 billion. That's hard to even wrap your head around. It's bigger than the economy of some countries.
It is. And the crucial thing our research team flagged is how this deal is structured. They're calling it a capital for capacity agreement.
Okay, break that down. What does capital for capacity actually mean? It's not just paying your cloud bill, right?
No, not like your usual cloud contract where you pay as you go. This is different. The AI lab is essentially putting down $38 billion upfront.
Prepaying?
Effectively, yes. Prepaying to lock in guaranteed priority access to hundreds of thousands of the latest NVIDIA GPUs. We're talking the top-tier stuff, including the next-gen GB200s and GB300s that aren't even fully out yet.
Wow, so they're buying their way to the front of the line for the next, 5-10 years?
Through the end of the decade, is the report. They are securing their compute supply chain.
So that capital for capacity term, it sounds a bit like de-risking. Shifting the risk by just throwing massive amounts of capital at it. Is that sustainable?
Well, from the AI lab's perspective, it's absolutely a strategic de-risking play. First, it breaks any perception that they're tied exclusively to just one cloud provider or investor. They're diversifying their compute supply. Multi-cloud.
Ah, okay. So if one provider has issues, they're covered.
Exactly. Supply chain problems, price hikes. They've secured a dedicated pipeline elsewhere. It's about ensuring they have the sheer power needed for whatever comes next. GPT-5, GPT-6, these incredibly resource-hungry models.
So the competition isn't just about who has the best model ID anymore. It's about who physically has the secured, long-term access to the hardware needed to build and run it at scale.
That's the shift. It's raw power access, and this leads straight to that barrier to entry problem you mentioned.
Right.
If just guaranteeing your supply of compute costs tens of billions per provider, well, who can actually afford to do that?
Only the giants.
Yeah.
The trillion-dollar tech companies.
Pretty much. AWS, Google, Microsoft, and maybe labs closely backed by them. It locks in the power structure at the very top. For a startup or even a smaller national lab trying to catch up on foundational models, it's become almost impossible from an infrastructure cost perspective.
We're moving from innovation being the main bottleneck to, sheer capital and access being the choke point.
Yeah. But, this massive spending spree on hardware, it connects directly to a huge physical problem, a constraint.
Which is?
The energy bottleneck.
Ah, yes. All those GPUs need power. Lots of it.
An incredible amount. And this is backed up by multiple data sources. The scale of this GPU build-out is directly creating massive, really straining energy demands.
The numbers our team found are, frankly, they're quite alarming. Like,
Yeah.
U.S. data centers already used 4% of the entire country's electricity in 2024.
That's right. And to give you a sense of scale, that's about the same amount of electricity an entire country like Pakistan uses in a year.
And that's now. It's not some future problem.
Exactly. And the projections. They show this is just warming up. Forecasts suggest data center power consumption is set to more than double by 2030. That's a 133% increase.
Doubling from an already huge number.
And some analyses, pretty well corroborated ones, suggest data centers could be eating up something like 12% of all U.S. electricity by as early as 2028.
12%. Just for computing. Let's pause on that. What does that do? I mean, the grid wasn't built for that kind of surge.
It's causing major strain. We're already seeing reports from utilities and major hubs struggling to approve new connections for large facilities. Not just data centers, but factories, too. They physically can't supply the power reliably.
So it's delaying other economic activity.
In some cases, yes. And utilities are having to plan billions in upgrades, new power lines, new generation sources.
And guess who pays for those upgrades in the end?
Well, usually it gets passed on to consumers, right? So higher electricity bills for everyone.
So the efficiency of these AI models, it's not just a tech spec anymore. It directly impacts household budgets and national infrastructure planning.
Absolutely. Lack of efficiency in AI is now a pocketbook issue and a grid stability crisis. This huge capital investment in compute is creating very real, very physical pressures on the energy system.
Okay, so we have this massive infrastructure build-out facing energy limits. Moving up the stack, let's talk architecture. How are these systems actually being designed? The research suggests a major shift here, too, bringing quantum computing into the mix, but maybe not how people expected.
Yeah, it's fascinating. We're seeing a move towards a hybrid model, and it's driven by a fundamental physics problem with pure quantum computing. Our team calls it the Mercurial Quibbit problem.
Mercurial Quibbit. Okay, I like that. What's the issue?
Well, think about those GPUs we just talked about. They're complex but relatively robust, right? Industrial grade. Quibbits, the basic units in quantum computers, are, well, they're incredibly fragile, like exquisitely sensitive.
Sensitive to what?
Pretty much everything. The tiniest bit of noise, a slight change in temperature, stray magnetic fields, anything can cause them to lose their quantum state. It's called decoherence.
And decoherence means errors.
Massive error rates. The quantum calculation just falls apart. This inherent fragility, the sensitivity, is why building a large-scale, fault-tolerant, pure quantum computer has been so incredibly difficult. It works in theory, but in practice, keeping qubits stable is a nightmare.
So the engineering workaround isn't necessarily to build a perfect quantum computer in isolation.
Exactly. The clever solution, being demonstrated at places like Oak Ridge National Laboratory or RNL, is to use classical computing power, specifically the brute force of GPU and CPU clusters, to actively manage the quantum system.
So classical computers babysitting the quantum ones.
Sort of, yeah. Think of the quantum chip as trying to do the really complex, quantum-specific part of a calculation, but it makes tons of errors. The classical GPU cluster is running alongside it, constantly monitoring, predicting errors, applying corrections in real time, trying to keep the qubits coherent and on track.
It's like a control system for the quantum process.
A very sophisticated, very fast classical control system. And this hybrid approach leads straight to a potentially huge strategic advantage for certain players. Because the software needed to manage this complex dance between the classical GPUs and the quantum processor, the key orchestration layer is NVIDIA's CUDA-Q platform.
Ah, CUDA again. Just like they dominated classical AI training with the original CUDA.
Exactly the same playbook. CUDA-Q is being positioned as the essential software gateway. It's the common language that lets researchers run the quantum algorithms and the classical error correction algorithms on the GPUs simultaneously.
So even if quantum hardware eventually becomes incredibly powerful,
the path to using that power effectively, at least in this dominant hybrid model, runs through NVIDIA's software and, by extension, their classical hardware.
They've managed to ensure the most profitable part. The software-controlled classical compute remains essential, even in a quantum future. It's quite a strategic lock-in.
It's a very strong position. And this isn't just theoretical anymore. The research team highlighted real-world applications starting to emerge. For example, there was a demonstration in South Korea using what's called Continuous Variable Quantum Enhanced Reinforcement Learning, or QRL.
Okay, QRL. And what did
Yeah.
they apply it to? Not particle physics, I gather.
No, something very practical. Managing residential HVAC systems and home energy use.
Seriously, quantum computing for thermostats.
Well, for optimizing energy use across a whole system. They fed it real-time data occupancy, weather, electricity prices, and the QRL system, running in simulation, managed to cut power consumption and electricity costs by over 60% compared to standard methods.
60% reduction. That's huge, especially given the energy bottleneck we just discussed.
Precisely. It shows that this hybrid quantum classical approach, even in its current noisy managed state, is starting to deliver tangible benefits for high-impact efficiency problems. It's moving from the physics lab towards real-world utility.
That focus on utility brings us neatly to the next point, standards. The quantum field has felt a bit like the Wild West, hasn't it? Everyone claims big numbers, Quibbit counts, quantum volume, but it's hard to know what they actually mean in terms of solving real problems.
Absolutely. It's been confusing, with vendors using different, often incompatible metrics. You can't easily compare systems or trust the claims. That's why the work by DARPA, the U.S. Defense Advanced Research Projects Agency, is so important. They've announced Stage B of their Quantum Benchmarking Initiative, QBI.
QBI. And the goal isn't just more metrics, right? It's about defining what useful actually means.
Yes, exactly. QBI aims to establish a standard for utility-scale operation, and they define that very practically. It's the point where a quantum system's computational value exceeds its cost.
Value exceeds cost, so it has to be better and economically sensible compared to just using a classical supercomputer.
Right. It forces the conversation away from just theoretical speedups to actual demonstrable cost-effective advantage on problems that matter.
That feels like a turning point.
Yeah.
Moving quantum from, a kind of mysterious R&D effort into a proper, structured, auditable engineering discipline.
That's the goal, making the investment justifiable. And DARPA isn't just talking concepts. They've laid out a public roadmap for QBI, currently stretching out to 2033, to reach that verified utility threshold.
So a clear path, clear milestones.
Yeah, it provides structure. It helps governments, researchers, companies know what they're aiming for and how to measure progress credibly. It's about building trust in the field as the investments get larger. Midsection CTA.
Hearing about this push towards practical utility in real-world applications is fascinating. And if you're finding this deep dive on Tomorrow Unveiled insightful, this is probably a good moment to ask. Please take a second to like this video if you're on YouTube, subscribe to Tomorrow Unveiled, maybe even hit that new hype button. It really helps us reach more people.
And definitely turn on notifications so you don't miss our future updates.
Absolutely. We also love hearing from you. Whether you're watching on YouTube or listening on your favorite podcast app, drop a comment. Let us know what you think about this idea of AI getting deeply involved in critical industrial systems like the power grid.
Which actually is exactly where we're headed next.
Okay, so if infrastructure is the foundation and architecture is the blueprint, the application layer is where the rubber meets the road, right? Where AI starts doing real work in the physical world. And the research suggests a big shift here, moving beyond soft digital tasks.
Definitely. We're seeing AI move from things like optimizing online ads or powering chatbots to tackling really hard physical industrial problems, especially in what's called critical national infrastructure, or CNI.
CNI, like power grids, water systems, transportation.
Exactly. And the prime example highlighted by our research team is a major collaboration involving the energy grid. A big Japanese conglomerate is working with the Southwest Power Pool, that's the organization managing the grid across 14 states in the middle of the U.S.
Okay, why bring AI into the power grid now? What's the problem they're solving that existing systems can't handle?
It boils down to what the researchers call the green grid problem. Our electrical grid was built for predictability, big, stable power plants running 24/7.
Coal, gas, nuclear.
Yeah.
Steady output.
Right. But renewables, wind and solar, they're inherently variable, intermittent. The wind doesn't always blow, the sun doesn't always shine.
And those fluctuations can destabilize the grid.
Massively, especially at scale. Imagine a huge drop in wind power across Texas, or unexpected cloud cover moving over solar farms in Oklahoma. Those sudden changes in supply can cause frequency dips or surges that traditional control systems, designed for slower changes, just can't react to fast enough across such a wide area.
So AI becomes essential for renewables.
It's becoming the key enabler. The research strongly suggests that hitting ambitious decarbonization targets, getting lots of wind and solar onto the grid, might actually be unachievable without sophisticated AI control systems.
Why? What can AI do?
It can do real-time forecasting, predicting renewable output second by second. It can perform microsecond load balancing, shifting power flows instantly. It can even predict equipment failures before they happen. It provides a level of dynamic control that's just impossible otherwise.
So AI isn't just helpful here, it's becoming a necessity for the green transition.
That's the argument. But, and this is a huge but, this reliance creates an enormous vulnerability.
How so?
Well, if you give an advanced AI operational control over the physics of the power grid for an entire region, that system instantly becomes one of the most high-value targets imaginable for a cyber attack by a hostile nation or group.
Wow. So AI safety isn't just about preventing biased outputs anymore. It's about national security. It's about keeping the lights on.
Absolutely. AI safety and robustness become fundamental requirements for C&I resilience, which leads us directly to the next major finding: the urgent need for new, trustworthy governance structures, especially when AI moves into other regulated sectors.
Like healthcare, finance, pharma.
Exactly. These fields require transparency, accountability, auditability. You can't just have a black box AI making critical decisions. The research team detailed a specific framework called DAECC, that's Dynamic Agent Extension and Contextual Communication.
DAECC. Okay, that sounds complex. Let's try that analogy approach again. How would DAECC work in, say, a healthcare setting? Maybe AI helping a doctor with treatment plans.
Okay, good example. So imagine you have AI agents assisting doctors. DAECC has 3 key parts. First, the Adaptive Agent Extension Mechanism, or AAEM.
AEM. What does that do?
It constantly assesses the situation. If a patient presents with a complex, unusual condition, the AAEM decides, can the existing AI agent adapt safely, or is this novel situation too risky? If it's too risky, it flags that a new, specialized agent might be needed, or more likely, that human oversight is mandatory.
Ah, so it keeps humans in the loop for complex or edge cases. It ensures accountability.
Precisely. Mandatory human approval for critical steps is built in. Accountability isn't lost.
Okay, component 1, adaptive safety with human oversight. What's next?
Second is a SIFCOM, Sustainable Enterprise Framework for Communication. Remember the energy problem.
Yeah, all that data center power.
Well, AI agents communicating with each other constantly can also consume significant energy. If you have dozens of agents involved in a patient's care scheduling, billing, diagnostics, monitoring, they might exchange thousands of messages. SIFCOM is designed as a super efficient, lightweight communication protocol between these agents.
How efficient?
The research suggests it can reduce the energy used just for that agent-to-agent communication by up to 40%. It's about building sustainability right into the AI's internal chatter.
Okay, so energy efficiency baked in. And the third part?
That's CMIP, the Contextual Model Interaction Protocol. This is all about the audit trail. It's crucial for compliance in healthcare or finance.
CMIP. Why not just use regular logs? Databases.
Because logs can potentially be altered after the fact. CMIP ensures that when agents negotiate a task like the diagnostic agent proposes a test, the safety agent approves it based on patient history, the scheduling agent books it, the entire sequence, the context, and the outcome are recorded immutably.
Immutably, like on a blockchain.
Exactly. It uses a secure blockchain ledger. So if an auditor, or even a lawyer, needs to know why a specific decision was made months or years ago, the CMIP record provides a verifiable, unchangeable history of the entire process, including which human gave the final sign-off.
That level of auditable proof is huge for regulated industries. The research mentioned a first demonstration.
Yes, in mental health care, with a system called Mind Rewire Therapy. It showed how AI agents could adapt treatment suggestions in real time based on patient responses, while simultaneously ensuring every step adhered to strict ethical guidelines and compliance rules, all recorded via CMIP. It proves the framework is viable even in highly sensitive areas.
Okay, so specific frameworks like DAECC are emerging, but is AI also changing the broader landscape of compliance itself? GRC governance, risk, and compliance.
Absolutely. The whole field is shifting. We're moving away from periodic manual audits like checking compliance once a quarter.
The old way.
Right. The new requirement, driven by standards like SOC2 and ISO 27001, is continuous compliance monitoring, and AI is becoming the core technology to enable that. How?
AI systems can ingest real-time data streams from across an entire organization, system, logs, access records, network traffic. They constantly monitor for tiny deviations from compliance rules, what's sometimes called control drift.
So it catches small problems before they become big audit failures.
Exactly. AI is shifting from being part of the compliance risk to being the primary tool for managing compliance risk.
Are there other ways AI is being used in GRC?
Yes, quite a few are emerging. The research highlighted GenAI-driven policy creation, basically, using AI to automatically draft or update internal policies based on the latest regulations. Saves huge amounts of time.
Makes sense.
And also intelligent risk assessment. AI can analyze vast amounts of security data, vulnerability reports, threat intelligence feeds, and generate real-time dynamic risk scores for different parts of the business. Much faster and more comprehensive than manual analysis.
And maybe the most meta application, using AI to monitor AI. That's the final piece. Organizations are now deploying AI-powered governance tools specifically to watch their other AI models. They monitor for things like model drift, where performance degrades over time, or the emergence of bias in decision-making.
So AI policing itself, what standards guide that?
New frameworks are being adopted rapidly, especially the NIST AI Risk Management Framework, RMF, from the U.S. government, and the international standard ISO 40001. You need standards to govern the tech that governs everything else.
All right, let's go deeper now. Right inside the AI models themselves, what's happening at the core architectural level? The research pointed to some really fundamental breakthroughs, didn't it? Tackling long-standing ML problems.
Yeah, two really stood out. The first one addresses a huge hurdle on the path towards more general AI, maybe even AGI. It's called catastrophic forgetting.
Catastrophic forgetting. Sounds dramatic. What is it?
Think about how we learn. You learn Spanish, then you learn French. You don't usually completely forget all your Spanish the moment you start French, right?
Hopefully not. You might get rusty, but it's still there somewhere.
Exactly. But standard AI models often do forget catastrophically. When you train them on a new task, the new learning overwrites the connections needed for the old task. So the model masters task B, but completely loses its ability to do task A, which it knew perfectly before.
That seems incredibly limiting if you want AI that can learn continuously like humans do.
It's a massive barrier. So a research team announced a new approach, the nested learning paradigm, and the architecture they built for it is called HOPE-T. That stands for Hierarchical Optimizers with Persistent Embeddings.
Hope. Okay. How does hope avoid catastrophic forgetting?
It fundamentally changes how the model is structured. Instead of seeing it as one big block of memory that gets overwritten, HOPE views the model as a network of interconnected, nested learning problems. Different parts specialized.
Nested, like Russian dolls.
Sort of. And crucially, it incorporates different types of memory, short-term, medium-term, and long-term memory pathways, more like a continuum, rather than just one easily erased slate. This allows it to preserve older knowledge while integrating new information.
That sounds like a much more brain-like approach.
Yeah.
A big step.
Potentially a very big step towards models that can learn and adapt over time without constantly needing full retraining from scratch.
Okay, that's fascinating. What was the second architectural breakthrough? Something about graphs.
Yes, this one's about graph neural networks, or GNNs. GNNs are super important for analyzing connected data. Think social networks, protein interactions, supply chains, anything where relationships matter.
Right, how nodes connect to each other.
Exactly. And traditionally, GNNs use fixed methods to aggregate information from a node's neighbors. Like, they might take the average of the neighbor's features, or the maximum, max, or the sum.
Seems logical. What's the problem with that?
The problem is, real-world graphs are messy. Sometimes averaging information from neighbors is exactly the wrong thing to do, especially in graphs with what's called heterophyly.
Heterophyly.
It means connected nodes are often very different from each other. Think of that political example. Two opposing candidates might interact a lot online. They're highly connected. If you just average their features, you blur out the crucial fact that they represent opposing viewpoints. The mean aggregation washes away the important distinctions.
Oh, I see. Fixed aggregation doesn't work well when neighbors are dissimilar but connected.
Exactly. So the research team developed a new framework called Aggregation-Aware MLPs, or AMLP. And the clever part is, they stopped trying to design the perfect one-size-fits-all aggregation function.
What do they do instead?
They focused on making the representation of each node, how the node encodes information about itself, adaptable to the aggregation process. The node learns to represent itself in a way that anticipates how its neighbor's information will be combined.
So the node's self-description changes depending on who its neighbors are and what task you're doing.
Kind of, yeah. It makes the representation context-aware regarding aggregation. And the really impressive thing, this AMLP approach uses a very simple single-layer MLP design, no massive new complexity, yet It achieves state-of-the-art results on 12 different graph datasets for clustering tasks.
Simple but effective. Changing the representation was key.
Exactly. It shows innovation isn't always about bigger models. Sometimes it's about smarter architecture.
Speaking of size versus smarts,
Yep.
that brings us to efficiency and this idea of open source models catching up. For a long time, the perception was that only a few big Western labs had the truly cutting-edge models.
That perception is changing rapidly. The release of Kimi K2 Thinking, an open-source model focused on reasoning developed by a firm based in Beijing. Our sources are calling this a seminal moment.
Seminal. Why? Is it just that good?
It's performing incredibly well. On a tough benchmark called Humanity's Last Exam, which tests complex reasoning, Kimi K2 scored 44.9%. According to the analysts their team reviewed, that score actually surpasses some of the very latest proprietary models like GPT-5 and Claude Sonnet 4.5, at least on that specific reasoning benchmark.
Wow. Open source beating the closed giants on reasoning.
On that benchmark, yes. But it's not just the score, it's how they achieved it. Kimi K2 uses a huge underlying architecture, 1 trillion parameters, built using a mixture of experts or MOE approach.
1 trillion parameters. That sounds enormous, inefficient.
That's the clever part. With MOE, even though the total model is huge, for any single task or query, it only activates a small fraction of those parameters, in Kimi K2's case, around 32 billion.
So it has massive potential knowledge stored, but only uses the relevant experts for each specific problem.
Exactly. It combines the power of immense scale with the efficiency needed for practical deployment. You get top-tier reasoning, but without needing a nation-state's budget to run every single query.
That's a huge deal. It shows that cutting-edge performance and practical efficiency aren't mutually exclusive anymore, and that innovation is clearly global.
Absolutely. It demonstrates that non-U.S. research groups have effectively closed the performance gap, especially through sophisticated architectural innovations like MOE. The competitive landscape is definitely shifting.
So these powerful, efficient models are becoming more widespread, which logically leads to the final layer, the interface. How do more people actually use this power? The research highlighted Google expanding its Opel platform globally.
Yes, Opel. It expanded from just 15 countries to over 160. This is a big strategic push.
And Opel is a no-code AI builder.
Pretty much. It's aimed squarely at what they call the citizen developer. Think of a marketing manager, a financial analyst, a scientist, someone who's an expert in their field but isn't necessarily a professional programmer.
So lowering the barrier to creating AI applications.
Dramatically. Opel lets these users visually drag and drop components to build quite complex multi-step AI workflows or mini applications, all without writing traditional code.
Give me an example. What could a non-programmer build?
Well, imagine that compliance scenario again. A compliance officer could potentially use Opel to build a workflow that automatically ingests regulatory updates, uses an AI model, maybe even one built on MLP principles, to analyze internal documents against those updates, flags potential issues using something like the DAECC logic, and then generates a draft report for human review.
All visually, without coding.
That's the promise. It's really a battle for the next major platform layer. Think about the impact of the App Store for mobile phones.
Right, it created a whole ecosystem.
Google seems to be betting that the future of enterprise AI isn't just the chatbot interface, but these shareable, customizable visual workflows. They want Opel to be the App Store for generative AI applications within businesses.
So the interface shifts from just conversation to structure and process building, owning that platform. That's where the long-term value might be.
That seems to be the strategic bet. They want to own the place where AI gets integrated deeply into actual business operations built by the people doing the work. Hashtag outro. So let's quickly recap this whole journey through the AI stack on Tomorrow Unveiled today. We started down at the bedrock. Infrastructure. Saw those huge $38 billion capital for capacity deals reshaping market access, butting right up against that critical energy bottleneck.
Right. Then we moved up to architecture, saw the rise of practical hybrid quantum classical systems, largely orchestrated through NVIDIA's CUDA-Q, locking things in, and how standards like DARPA's QBI are pushing quantum towards real, measurable utility.
Then we hit the application layer. AI moving into critical infrastructure like the power grid essential but risky, and the emergence of governance frameworks like DAECC designed to bring transparency and auditability, especially for regulated fields like healthcare. Plus AI becoming foundational for compliance itself.
And finally, inside the models and at the interface. Breakthroughs like Hope tackling catastrophic forgetting, AMLP improving GNNs, the geopolitical shift shown by open source Parity with models like Kimi K2, and the push toward citizen developers with platforms like Opel.
Yeah, the core theme weaving through all of this. AI isn't just a cool tech demo anymore. It's becoming strategic foundational plumbing for, well, for everything.
The new infrastructure of the digital and increasingly physical world.
And it's happening fast. The research team's data points to a dramatic acceleration towards more powerful AI. One leading lab is apparently projecting significant scientific discoveries driven by AI as early as 2028.
2028, that's incredibly soon.
It is. And it's fueled by this reported steep drop in the cost per unit of intelligence, maybe falling by 40 times per year. Things are getting smarter, faster, cheaper, exponentially.
Which means that window we have to figure out the safety, the governance, the energy issues. It's shrinking.
It really is. And speaking of support, if you're listening to Tomorrow Unveiled on a service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could take a moment to leave us a rating and perhaps a quick review. It genuinely helps new listeners discover the show.
Definitely appreciate that. So let's end with that final provocative thought, tying it all together. We talked about AI becoming essential for things like the green energy grid.
Necessary.
But doing that simultaneously creates what might be the single most valuable, most tempting cybersecurity target on the planet.
A huge concentration of risk.
So the challenge is stark, isn't it? As these AI systems become indispensable for the economy, for national security, maybe even for physical survival, can we engineer safety, robustness, and governance into them as an absolute guarantee? Can we use things like DAECC, NIST AI, RMF, ISO 42001 effectively before we hand over the keys to our critical physical infrastructure?
That's the race. Can the safety engineering keep pace with the capability curve? That's the core tension defining the future we've unveiled this week.
A critical question indeed. Thank you for joining us for another deep dive on Tomorrow Unveiled. We'll catch you next time.